हेलो एवरीवन. सो दिस इज़ वेरी वेरी इंपॉर्टेंट कॉन्सेप्ट है. सो इसकी ज़्यादा वीडियो अवेलेबल भी नहीं है, मतलब ज़्यादा लोग डिस्कस करते नहीं हैं. सो लेट्स सी हियर. So first we will see what is second order system. So what is the typical transfer function of the second order system? Like it's like this is the transfer function, like v naught s upon v in s. So it is, this is the general form, k omega n square upon s square plus 2 zeta omega ns plus omega n square. So at zero frequency you have gain k. Okay, so this is your dc gain and the rest is your transfer function. Okay, so most important one is step response. We will see impulse response as well, that is also important, but this one is more important, step response. Okay, so now your input is of v in s uh, is v by s, like it is in v in t is v into ut. So this is your input v by s. So there can be four kind of response. So I should go to next page. There can be four kind of response. uh, so undamped, underdamped, critical damped, and overdamped. Overdamped. This factor, this is zeta that we call it damping ratio. Omega n is oscillation frequency. Okay, so for undamped system is zeta equals to 0, and for underdamped is zeta sorry, for underdamped is zeta less than 1. Zeta less than 1. For critical damped is zeta equals to 1. For overdamped is zeta less than 1. Okay, so undamped means there is no damping. So there is no damping there. So for this would be this, how this is how our undamped response would look like. This is how it goes. Okay, like this is your v naught t versus t graph. This is underdamped. And pole zero location, this is very important. Like everything that I am saying in this video is very important, and I will like where in the circuit analysis it will be used, I will tell you. Like I will deal one more question in the next video only. Okay, so pole zero location, for pole location would be this on imaginary axis and conjugate, complex conjugate. Sorry, conjugate only. So on imaginary axis we will have conjugate poles. Okay, for underdamped, this is how the response would look like. So it would go something like this. Sorry, it will keep on decreasing and will stabilize at this value. Will stabilize at some value. Okay, so this is v naught t versus t, and pole zero location. So for underdamped system we will have two complex conjugate poles. Okay, and for critical damped system and for overdamped system, like this is v naught t, this is completely oscillating, and this oscillates first and then settle down. So what will be this value? This will be k into v value, k into v. K is over dc gain and this is v, so k into v value will be there. Okay, and now in both of the cases it will rise and reach to kV value, but this critical damped response is faster. Okay, so the critical damped response is faster, and this one is slower. So it will rise something like this. Okay, it rises immediately, and it will rise something like this. Okay, so this is what this is. This is k into v value, and this is k into v value. Okay, and now pole zero location. This is important, very important. Like pole zero location is very important. So talking about pole and zero. So this, in this one we have two real poles, and both at one point only, like two equal real poles we have. Okay, and here we have two real poles but unequal. One is here and one is here. I suggest you to write it down if you haven't read the control system subject and you are only going for some analog profile jobs. So this would be really helpful. Okay, all these you need to know. So this is for step response. Okay, so now let me go to impulse response. Now we will see impulse response. Impulse response. Okay, now your V in is your V in T is something like this, V into delta T. Your V in S would be V only. Okay, so now I will not take your time. I will simply copy these, because these pole location are same in impulse response as well. Okay, these pole location are same, and this like zeta equals to 0 would be called undamped system only. Underdamped system, critical damped, the zeta value are also same. The only the response is different. So I will only draw the response again, and will simply take the reference from here only. Okay, so for undamped system, you know what is the zeta value, right? You know zeta is lesser than zeta is equals to 0. There will be no damping, and we will have two poles on imaginary axis. Both are conjugate of each other, and your response would look something like this. Okay, undamped, it will keep on oscillating. Okay, for underdamped zeta is lesser than 1, and you have two complex conjugate poles, and your response would look something like this. Okay, response would look something like this. Okay, it's decreasing like in this manner. Okay, and for critical damped and for over damped, critical damped zeta is equals to 1, and for over damped zeta greater than 1, pole zero location are same. Okay, so for critical damped the response is something like this, and for over damped response is something like this. Faster, this one is again faster. Okay, this one is slower, but in, let me draw it once more. Like in critical damped, it will reach the value like very fastly and then decrease. And if you're this is your pole zero location, if this one is very far, this A, this is B. If B is very greater than A, so sometimes in some books you can see the response of overdamped system is drawn something like this. They draw it like this sometimes, like they reach the value at t equals to 0 only, and then decrease it. Okay, if B is very greater than A, okay, then they can make response like this as well. But in our circuit analysis, this will be used. Okay, so these information you must know. Now one more interesting thing I will deal here. So just imagine your transformation is something like this. Okay, there is one electrical circuit is there. You find the transformation V naught S upon V in S. You see one 0 at 0 only, and two poles at some values. Okay, and your transformation is something like this. And now the input is V by S. Like we have step input here. Now, so you have a step input here. So now how will your response look like? Like in the previous slides that we have studied, so it would be like step response of second order system or impulse response of second order system. So impulse response of second order system. So it would be like impulse response of second order system. Okay. Yeah, I'm having a bit cold, so that's why it is there is some interruption in the video. Okay, so I'm sorry for that. So it is like impulse response of second order system. Why? Because uh, if you see, like V naught S would be S omega n square, S square plus 2 zeta omega ns plus omega n square into this V in S, and V in S is V by S. So over V naught S is V omega n square upon S square plus 2 zeta omega ns plus omega n square. So here what you can see, this is your output, and in impulse response case, and in impulse response case, like this is your V naught S upon V in S. So this was omega n square plus S square plus 2 zeta omega ns plus omega n square. Now this V in S would go here, this V in S would go here and will be multiplied by this one. So V naught S would be of same level. So even though we are applying the step input, if our transfer function is having a 0, and then even though we are applying the step input, our output response would look something like impulse response of second order system. Okay, you got this point. So this is very important point. So this video is very important. Like I will deal like I guess I should deal the question in this video only, or I should make a separate one. I should make a separate one. So first you see this concept and then see the next video. Okay. So so in circuit analysis where it will be used, that will be clear in the next video. Okay. So you need to know this concept. Okay. Thank you.